All right. Hello and welcome, everyone. Kat, go ahead and intro us in whenever you're ready.
Welcome, lads and ladettes, to Aether Roundtable number 96, The Wizardry of Stellarium.
Nice. Excellent. Is that Ken finding his lighter?
Yeah, we're helping Ken search for it right now. The search continues on as usual, but we're going to get started with the Stellarium Prezi here. So this is a really interesting one and a subject that's come up quite a lot recently, especially with the celestial theody being so prevalent. Everyone wants to know about Stellarium. How does it work? What is it? What is the true position of a star? What do all these terms mean? How do they relate? Can you even map the stars? Where is the star? What does it mean exactly? So we're going to kind of go over the terminology tonight and go over the backbone of Stellarium so we can all understand what it is. Is Stellarium as a tool, or as an almanac reference, a mutually exclusive proof of the globe as we've been told? Well, we're going to dig into it tonight and see what exactly it means to use Stellarium and what drives it, what's under the hood. So without further ado, Shane, whenever you're ready, good sir, let's begin the journey.
Nice. Yeah, so this is definitely brought on by the celestial theodolite and our arguments therein, because when we're using a third-party reference or a true position reference, the opponents seem to lose their minds and start saying, well, as long as you represent it spherically, that's the globe. They cannot distinguish anything like an abstract coordinate system, right ascension, declination, latitude, longitude. All that is globe to them. That equals globe Earth. So is that the case, or is it based on observations, right? Stellarium at its heart is just matching empirical observations. So it's taking the hemisphere of observability that everybody has, and it's showing you your portion of the celestial sphere. At its backbone is the celestial sphere. That's pretty much what it is showing you. That's what right ascension declination is in relation to. That's describing the celestial coordinates. So we should go into the celestial sphere real quick to see what that is. It is, of course, one half of the two-sphere model of the cosmos. We have your terrestrial and celestial spheres. That's how the globe does its magic. That's how the whole modern model works. That's how modern celestial navigation works, the two-sphere model of the cosmos. So this is, of course, one half of that, the celestial sphere. If you go to Wikipedia or the regular mainstream, this is how they define it. An abstract sphere, so not real, has arbitrarily large radius, meaning infinite, and is concentric to Earth, meaning it's geocentric and around the observer. So we have a abstract, viewable hemisphere of infinite radius, concentric, specific to the observer. That's what the first line means. And then it says, all objects can be perceived as being projected, and it puts them on the inside of the sphere, and it is, of course, a hemispherical screen. So digging into that just a little bit further, the way it describes as a infinite radius, so arbitrarily large radius, just is another mathematical convention for describing a flat plane. So you have stars exhibiting flat plane angles off the flat plane, which is represented in an infinite sphere, or a sphere of infinite radius, of arbitrarily large radius. So we can reference with coordinates, but again, it's just a conceptual model. It has no real radius. It goes on forever, and it effectively then is just infinite. So you have what is modeled as stars, as not coplanar with, but parallel to the plane of the Earth. That's what the celestial sphere is emulating at its heart. So you have the plane Earth, and then this plane of stars above that. And these angles are represented as such, because in the celestial sphere, they just take infinite tangents to anything in the sky. So they put you on the conceptual sphere in the middle, and then anything around here, they'll just draw a tangent to this star, and then that's what they use. So it's exactly the same as a flat plane angle baseline, and just taking elevation angles to the stars. Again, if we're going to play around with the conception, you can use it in infinitely, a radius of infinite, a sphere with infinite radius or a flat plane are synonymous. They're both coordinate systems based on angles to the stars, and they're both just based on only ever a single hemisphere of observability. You're only ever observing half the sky. That's the same for both models so far. Now, sure, it uses a spherical coordinate system to represent data, but does that mean that data exists only as a sphere? No. If you translate it to cylindrical coordinates, does that mean it only exists as a cylinder? No, that's retarded. If you translate it to rectangular coordinates, does it now only exist rectangularly? No, also retarded. These are simply representations of observation. So the observation itself is separate from the coordinate system in which we choose to represent it. That should be obvious, but I don't think it is. I think we should shout it out that we're just representing it in these coordinates.
And something real quick to add on coordinate system transformations, you'll notice there in the diagram, the z-axis is the common alignment for all the transformations. So as long as you have a symmetrical z-axis to whatever shape you want to transform to, there's a formula that will give you the correct symmetrical transformation to any geometric shape. I got a whole book on it that goes through. Yep, you got it. Yeah, the parabola, hyperbola, cone, cylinder, every type of shape that you can imagine is intersected by the original rectangular coordinate system planar. So
yep,
as long as you know the formula, you can do it as long as they have an intersecting point. So
orthogonal coordinate systems are all interchangeable, right? They're all, this is where we said we can exhibit them in Cartesian simultaneity. No matter which one of these you're currently presenting in, it doesn't change the source data.
Can I ask a question real quick?
Yeah. Absolutely.
All right. So when it comes to the terrestrial and celestial sphere coordinate transforms, what exactly is it? Is it one transform to another? And if you're going to get to that, then I'll just wait.
Well, it's right ascension declination to latitude longitude. That's what it is. That's the one-for-one correlation. Because of the basis of the ground position, you can translate this sphere to this sphere directly, and that's that's what's actually behind modern cell nav, and it's a big part of what Stellarium is doing, right? This is from Stellarium. My model of the celestial sphere is just a Stellarium printout, should be noted. But over here, you can convert right ascension and declination directly to longitude. So the coordinate system itself is actually represented in so declination is like elevation, so it's just in degrees, right? But right ascension declination is in time, so it's like degrees, minutes, seconds. So that's how they represent that. And then when you're trying to convert that, you're converting right ascension to longitude and declination to latitude. So declination to latitude is like one for one. It's super easy. Right ascension to longitude is the hour angle transformation, requires your local time in a comparison to a Greenwich Mean Time usually, and it utilizes the 365 degrees. So it takes 24, and then you get 15 degrees per minute, or sorry, 15 degrees per hour, which we then translate into 4 degrees a minute when we do celestial observations with the celestial theodolite. So it's all interconnected, essentially. It's all interwoven and interchangeable and back and forth.
But right, but I'm just thinking like to the equivalence. So it would be, we treat the terrestrial sphere as like a hemisphere, and then the field of view, where stars or anything go out of our field of view, or our rate, our semi or our hemisphere, right, of vision, then you can just treat it as like a negative coordinate, as if you were going like past the equator, essentially, like on a ball. In terms of the equivalence, it's almost like you have two hemispheres right next to each other. You can still treat it like a negative coordinate system.
Yeah, so the mathematical mapping of when it reaches the bottom of the arc of your vision, or when it goes beneath the Earth as a ball, is going to be mapped as the same function. So
right.
Yeah, I think he's trying to draw a parallel between negative coordinates on the graticule and latitude and longitude to represent the hemisphere you're not in, versus negative coordinates in the celestial coordinate system to represent a star you wouldn't see. The parallel should be, though, it's to represent things you can't see. So you can never see the other hemisphere. You can never see the star that's setting. So it is like similar that way, where you're just representing the other component mathematically with a fictitious mathematical southern portion.
Right. Like it's fictitious because you can't see it, literally. Like you can only do local measurements. Right.
Yep.
Yeah. And another component from that would be like, if you're looking at it from the Stellarium point of view, right, you have like this like God's eye view perspective of the system, but nobody sees that. You would only be able to reference the stars that are relevant, to your hemisphere. But because the way that it's mapped out with taking a snapshot of where they were on the first point of Aries and then adding 15 degrees per hour to that, they can just project out, where they would be. So it gives the appearance of like, globularity or whatever, but it's just the same cycle. You just see it all at once from an outside perspective, where you can just reference it at any time because time equals position of the star.
Right. And all you have to do is take the first reference point. And
yeah,
then,
that's known as
said,
like an
project it out
epoch.
from there.
Remember, we had an epoch, so that's like a universal reference point where if we all decided some measurement was 0, we could all start there. We could take measurements from there. It's just so we can align our measurements uniformly. So
like a UTC is the epoch, right? Essentially.
Yeah, for time zone, sure. If we all use UTC, how much easier would life be? If we all just did everything in scheduling, if we scheduled our Discord events with the Check Boys and UTC, we never would be an hour late, When we mentioned the first cusp of Aries, we mentioned that a lot in relation to Stellarium, so I just got the Google definition here. Also known as the first point of Aries, which is the location of the March equinox and serves as the 0 point for right ascension in celestial coordinate system. So just like I said, it's a point to be designated 0 from which other measurements can then be made. That's its only purpose. The fact that it's in Aries is irrelevant. The fact that it was in Aries, that's compared to all of this is irrelevant. It's just a 0 point, as we just went over. So what that looks like spread out is this is just a star map. Here's the first point of Aries. Here's the all the other zodiac symbols. Here's the ecliptic of the sun, and I just represented it on an AE projection. And what this is now that these are where the stars are, right? Remember, the stars never change in distance to relation to one another. They spin as an equidistant web and never getting further or closer from each other. And they literally never, ever change, right? So this whole equidistant web of stars just spins like this. So what you get is something like this. If you know where all these stars are, then you map them out according to this first cusp of Aries, first point of Aries, and then you make 0 to 360 degree measurements in relation to that 0 point. And as you can see, they spin around and the timing changes. And you can see if this is a day, 24 hours divided by 365 degrees gives you your 15 degrees per hour rotation, which is what we're looking at. Broken down further without the zodiac, you get something like this, right? All the stars in their known positions, rotating around the Earth steadily in their same latitude rings, never ever changing, never growing distant or further away from each other. And this is what Stellarium is mapping. This is what it's showing you. Depending on your latitude or where you are on the graticule, it shows you your specific half chunk of the sky from wherever you are. And we can show that because at its heart, this is from the Stellarium source code. It just says uses geocentric coordinate system for all internal calculations to simulate the night sky. Celestial coordinates, right ascension and declination, are transformed into horizontal altitude and azimuth relative to the observer's position. So altitude and azimuth is like the flat Earth coordinate system. If we didn't touch on that, it's literally how we observe the sky. It is this, right? If we have a flat plane and we see half of a hemisphere, and we can take, the sun angles and the circles that the stars and the celestial objects take, this is what can be marked as the horizontal coordinate system. It's literally the coordinate system based on you observing a single hemisphere from a flat plane and then making angular measurements therein. So if we're describing the backbone of Stellarium, it says something that it says, hey, we're using this geocentric coordinate system for everything. We use only right ascension and declination, which is what I said at the start. It's at its heart, showing you just the celestial sphere. And we represent the celestial sphere, which is viewed and observed hemispherically. We choose to reference it spherically. Now, because we reference it spherically, does that mean it only exists as a sphere, as we started out with? No, that's retarded. It's just represented spherically. And in fact, what we should have pointed out is the only difference between representing something hemispherically and spherically is this one coordinate has a negative value when it goes below the fundamental plane. It's the same reference system, same spatial reference, same variables, same proportionality, same everything, except it can go below the fundamental plane. That's the only difference between these two. So can flat Earth use the right ascension declination, the celestial coordinate system? Of course we can. That would be equivalent to saying every time you look up, everything you see up there is a globe measurement. Now, that's different from saying that the sky is globe evidence. They can blend that into their model. The whole model is based on their observations of the sky, sure. But the observation itself is model independent. You can't say all observations of the sky are globe, all observations of the sun our globe. And that's currently where the bar is at for our globe Earth friends with Stellarium usage as far as the celestial theodolite goes. So, haha, you can't beat us with that because it's globe. And as we see here, it's not globe. What it actually does, and this is with the Stell core function, it does this. So this is the updating your position when you click on maps, and that's of course geodetic coordinates, which we know Latin long. And then when we're doing the alt as, it just does convert equatorial based on the observer's geocentric position, and it assumes geocentric coordinate system for all calculations. And then finally, we have the steel geodesic grid, which is what we put on when we see the equatorial grid, which we're going to demo in a second. But it's conversion from geodetic, latitude and longitude, to geocentric. So latitude and longitude converting. And then it's essentially putting observations stored in the celestial sphere, which is over here, into the local alt-as grid of the observer. So it looks a lot like this. What it's doing is representing angles to local observers at apparent heights, and it's representing them in a ever-changing, moving spherical grid format, which we always argue it puts the whole grid in a sphere of radius 3959. And if you do that, then this is the math that would give you the distance at the highest point. When the star is furthest away from you, it's 6218. That's the furthest away it could be. Of course, it changes as it goes from zenith to nadir as it sets. And of course, it's just representing your hemisphere. So what it would look like in actual terms, with if you're looking at the flat Earth, if everyone sees half the sky, this is what Stellarium is showing you. It's doing it a little differently when it's in the application, but it's choosing this projection. If it was just choosing this projection instead of a Mercator, this would be identical to what Stellarium is showing you. This is what we're using it for. This is what it's running on. It'd be like if we are in this image right over here. Now, are we moving along this Mercator map, or are we moving along this conceptual sphere? See how it's representing the movement in both simultaneously? Well, according to our globe Earth friends, this is now a square sphere. Because it's in this coordinate system, this is where it's represented. And the truth is, no, it's in neither of these. This is just being projected onto two projections simultaneously, an orthographic globe and the Mercator square projection.
No,
So
we live on
it
a
moving
square.
back and forth. Like, according to them, this is a conundrum. Now we know Earth is a square. No. So if we go back to what we were talking about within Stellarium, you can see we have settings here. When they say, oh, look, the star's beneath your feet, that totally ruins your whole thing. And it's like, well, does it? You have your azimuthal grid, which will show your local alt-as, and you have your equatorial grid, which will show the celestial poles as described by the relation to the celestial equator. So you'll see the north concentric pole and the south pole. If we look at this video here, we can see in Stellarium, if you were to open it up and start processing, this is what it looks like. This is what you would see. This is how it looks like. This is actually an orthographic view. So you can see we're already representing it in this spherical coordinate system that we're talking about. This is how it represents the celestial observations. It's literally converting right ascension declination to local alt-as right here. Here's our azimuthal grid. As with the first thing, it puts the zenith right above the observer. It's always directly above you. It's just an equispatial grid from which you can make measurements. And this is the top view. And this is what it looks like with the azimuthal grid function on. Now we can turn that off and we can put the equatorial grid on, which will show our celestial poles. And you can see it change a little bit. We no longer have the zenith above us in a concentric circle, but it's off to the right because we're at 45 degrees north latitude. So this is the only thing Stellarium is doing.
It's awesome. And you said based on local UTC time, depending on the observer location, right?
Yep, you can see UTC is clocking down in the bottom of all Stellarium observations. It's always running. It's always using UTC.
Stellarium works everywhere, stupid flurf. Yeah. Well, it's referencing the same epoch.
What a brilliant demonstration of the equivalence there, Shane. Because we're always told like, oh, can't do it. It's literally built into the primary, so-called mutually exclusive tool.
Yep. And all it's doing is referencing where the stars were at some point. So it's like, when we had our presentation on longitude and they did the whole book and they were like, oh, we created the chronometer. So now we can sail the seas. And it's like, well, no, the story actually said they created the chronometer and the nautical almanac. And those two together, they could then sail the seas. So chronometer is like an afternote. What they really needed was the nautical almanac, meaning the zero reference point of the epoch for all the references for the positions of the stars they were then going to be referencing to get themselves home when they couldn't see land. That's what it was. So that's what Stellarium is doing. When we're referencing a true position, this is what we're using it for. We're saying, hey, relative to the epoch of zero on the first point of Aries back when all this was measured, raised you 340 degrees from zero zenith to get us. That's the reference that we're making. That's the only way we're referencing Stellarium. So does the globe own all observations of the sky? No. Does the globe own all positions according to the nautical almanac? Hard no, right? So all of the argument that, oh, well, actually, if you choose to represent it spherically, then duh, it's a sphere. That just shows that our globe Earth friends have trouble separating concepts like spherical coordinates, the graticule, latitude, longitude, right ascension and declination, and the globe. If you throw in a geodetic ellipsoid datum in there, they're all sorts of confused. But don't fret, it's by design, right? They designed it to be confusing to get them to react exactly like that so that people would think that they live on a globe. All the way that we use Stellarium and is with first celestial navigation is the two-sphere model, circles of equal altitude based on concentric circles, right? Your observer, your concentric celestial sphere from the observer, the conceptual terrestrial sphere that you're supposedly living on, from which they translate measurements to and fro. When it comes down to it, it's just this abstract sphere of coordinate systems that they then prescribe to get this graticule, which is the orthographic representation of the one-for-one correlation of the geographic to the celestial. And if you look at how they represent it, you know, if we were to say because we did this, now everything is a sphere, that would be asinine. This is just spherical coordinates. This is a good slideshow I had from before showing how you can represent things spherically. Now, does that mean that they are in a sphere in reality? Of course not. You can take what is observed as a rectangular observation and represent it spherically, and then do some transforms in the spherical coordinate, move it around, and then translate that new position back to the rectangular coordinate system with a lossless conversion. There would be no difference, right? Just because you can do math with spherical coordinate system doesn't mean that that's what's observed. This is how reality is observed. If you look at even how they represent the celestial sphere, it's with hemispherical planar observations and then a latitude-dependent circular arc. At the equator, you get these circles, right? They're flipped based on the latitude. Under the North Pole, they look like this. And again, this is how it's describing it. On with a flat plane, a fictitious southern portion, and the absolute observable circular arcs that we see in the sky that everyone sees everywhere you go. Another one where they convert North Pole, the celestial coordinates get represented like this based on your latitude. This is like the straight Wikipedia entry where you can see the way they choose to represent them is with a dude standing on a flat plane looking at a hemisphere of observability around him. And you see that that's how they represent it everywhere you go, every time they talk about it. And then when they do math, they just pretend that this circle is around this circle and everything works out. So again, all they're representing here is this, right? The actual observation that we make in our alt as coordinate system, remember that? And then they convert that to a central reference point with an equator using right ascension and declination. And that's how we get the modern two-sphere model to be observed in Stellarium by referencing our nautical almanac on the first cusp of Aries at a certain time around the Earth. There you go.
Well done, lad. I like the updated demonstrations of the coordinates moving together, showing the equivalence and,
that's dope.
and the Stellarium recording update, man. Great job.
Nice. Thank you, dudes. Questions, anyone?
Very, very concise.
Or you go first.
Yeah.
I was gonna say no questions, but I wanted to go over a couple of definitions here in a minute. So if you guys want to do questions first, and then we can go over some of the things I wanted to add some extra clarification to.
Okay. Well, I was gonna say because maybe my question will be addressed in what you're about to clarify. So who knows? You want to do that first?
Yeah, sure. All right, let me pop open a screen share real quick.
Yeah, because really my question is kind of like a tertiary question for the future anyway. So.
All right, you're a tertiary.
You're a tertiary question for the future.
All right, so regarding the celestial sphere model, right? Because we know our boy Petals supposedly merged the celestial and terrestrial sphere, mapping out 8,000 locations all by himself, which is actually impossible. And if anyone believes that, is that's that's crazy. There needs to be more documentation on that story, because in order to map those out, one would have to take a zenith measurement on said epoch. So how this man was taking these zenith measurements to relate a star to a terrestrial position on the ground at a specific point in time over 8,000 locations is, you know, you guys figure that one out. But anyway, what I just found out recently was about the Japanese and the Chinese stuff with navigation, and how they were all geocentric flat earthers, and the model that they had here was represented by a flat Earth. So, and then this outer ring here is the celestial sphere, and then what you see here would be like the terrestrial equator equivalent around these little hemispheres. And then each continent had its own hemisphere that you would see this flat disk of stars above you that rotates in a circle. You would see that projected down into your, into your hemisphere of vision to create the celestial sphere model. So this is what the Japanese and the Chinese and other Asian cultures were using for their navigation and celestial navigation and stuff. So when it came to the 1400s, when the Chinese were doing a sailing expedition around the world, and they went all the way to the south to use 2 stars to try and finally get the ground positions there so that they could map everything out from there. They were doing it based off of this system, and then about 200 or 300 years later, the Royal Society shows up in Japan, and they're like, yo, that celestial sphere system you guys are using? Well, actually, there's negative coordinates, and that's because the Earth's a ball and the heavens are physical. And by the way, Newton calculated the mass of the Earth and the gravitational potential between the sun and all that. So like they came through with like the physicality of the heavens, and then just added negative coordinates to where the stars weren't. But because they had unified where they would be with their chronometer, they, as long as you knew your time, guess what? You knew that star, what star you were looking at that angle. So that's how they did all that. And then one other thing I wanted to define was geocentric coordinates, because this is the backbone of everything, like the almanac, Stellarium, celestial navigation. Everything you ever want to reference comes from this right here. And this is from the explanatory supplement to the astronomical ephemeris and the American ephemeris and the nautical almanac. So people were writing to the British Crown, and they were like, yo, how did you guys come up with the almanac and the corrections and all this stuff? Like what went on there? And they were like, oh, we'll give you guys a history of it. So here's how we did it. So this book is from said history from the Crown there, and they tell us about the geocentric coordinates. And it is a place of a star is a geocentric position is referred to the true equinox or the latter date, which is when the star would be observed. It differs from the position of where the star is actually observed by the effects of refraction and the diurnal aberration. Geocentric parallax is, of course, negligible. The unobserved position is therefore completely comparable to the apparent place after correction for instrumental error and refraction and diurnal aberration. So what they're saying here is, when you make a zenith measurement of a star, there's the least amount of refraction possible. So if you were going to try and relate a star to a position on the ground, you wouldn't do it from being like, 70 degrees and being 30 degrees off and trying to be like, it's probably around here. No, you want to get that sweet 90-degree relationship. And the best they could get is like 89.9999999, because the star is always moving and it's refracted, etc. Right? But to get the best optimal conditions for the snapshot to relate that star to a position on the ground for this epoch here that we're going to be referencing for our 0 point, they make these zenith measurements on that night, and wherever that star is, that's the snapshot that they're using for. So these are done by single observers at different locations. So do single observer zenith measurements, and then adding 15 degrees per hour to those is that mutually exclusive to anything? Does that tell us anything about where we live in a way that, can be explained in another way?
Did you repeat that?
What? Sorry, Beasticles distracted me.
I distracted myself too.
Yeah. So the way that it's presented is like, it's mutually exclusive to a globe, but like all they've done is take single observer zenith measurements and then tie them together with a snapshot and then add 15 degrees per hour to them. Does that tell us
Right.
anything about where we live? Like it's not a prediction of like, oh, it only works because of globe. It only works because you have a reference point and you added 15 degrees per hour to it, which eventually makes a circle.
Yeah, to be fair, without a reference point, like if I told you my right ascension declination for that star, you'd be like, okay, but when I find it, like it has a different meaning because we're not referencing the same 0 point. You wouldn't be able to find it based on the coordinate system, right? So that's why, and it's supposed to be unifying between models. So to say all of a sudden it's exclusive to yours is asinine.
Yeah,
that is true.
yeah, these are the kind of things that are argued. It's just basically rhetoric. So understanding the backbone of how these tools work and what they're doing is extremely important, because once you know that, you essentially can't be gaslit into, not using something because you think it represents mutual exclusivity of the shape of the earth, even though the backbone of it couldn't possibly tell you that.
Like right now, their argument is, well, the celestial theodolite is moot because Stellarium equals globe. So what they're saying is all observations of the sky are ours. They're forgetting that they're trying to refute the actual celestial observations of the celestial theodolite, which overwhelmingly verify flat each and every time as they try to show the surface of Earth is not curving, right? That's the whole point. And I think that it was intentional on Dr. Mike's behalf to use Stellarium and what was, quote, globe tools to disprove the globe. We can use the accuracy with the veracity of the position of a true position of a star for everyone at the same reference point to disprove that the Earth is not actually curving. That's what we're doing with it. So it's probably super painful for them to have their tool taken away and then also turned on them to betray them so hard. And that's why they're at this current point where they just point and say it's sphere. So
Yep. All right. I think that, let me check my notes here. Single observer Zenny measurements. Yeah, that's all I wanted to cover. And the Japanese and Chinese navigation stuff.
yep, this is very much an addendum presentation to supplement the celestial theodolite current spreadsheet battles, because their current argument has defaulted to just this. So thought we'd wrap this one up for everyone.
Yeah. So to close on a quote from Copernicus, go ahead, Beast.
Yeah, I just wanted to ask the certain question. So, I remember when you had the depiction of like the radius being 3959 of your observer's field of view, essentially. Like you treat the sky as like, okay, it's 3959, and then you're just basically traveling on your horizontal. I'm paraphrasing. Like I had the question in my mind earlier, but what I was asking, you said that Stellarium pretty much depicts it in this way. Is there a spot where you can kind of see that in Stellarium code that you found?
Yeah.
Where it shows the height of the stars?
No. So it doesn't show the height of the stars.
Oh no, they'll never tell you an altitude of a star. They'll only refer to the altitude of a star as an angle.
Remember, it's infinite and it goes on forever and it travels a billion light years, right? So the code is not going to show you an infinite distance. The code shows you no distance. Remember, the celestial sphere has an arbitrarily large radius, meaning infinite, doesn't matter, negligible. So that's how far all the stars are at any given point, infinite or negligible.
Yeah, what it does do, Beast, to answer your question though, the geocentric coordinate system transformation puts the observer in the center. So like you can think of this outer shell. You got my screen up?
Yeah, I'm looking.
Okay, think of this outer shell as the surface of the Earth that they want you to believe in. Now, the observer's on the outer shell here, making his observation or making his zenith measurement, right? But they need to use the geocentric reference point. So they're going to do this transformation here, where they're going to put this observer here, down at the bottom now. Now we're inside of the Earth at the center. And up at the top of the Earth, right here at this 3959, is going to be the star. And then it's gonna, as it would move relative to your lattie or however you move, 69 miles per degree, that relationship is going to be represented along that arc from this reference point. So they set the altitude to this in the geocentric transformation, although they'll never outright say it and they'll deny it and act like they're not setting it to that altitude. They're not setting it to that altitude, otherwise this wouldn't work, because remember, they need a common z-axis alignment. So they're saying that the terrestrial sphere goes from where this observer here is in the center to out here would be the equator, and then the celestial sphere would be around it, basically overwrapped at the same point, because they need to make that sphere of infinite radius useful. They need to bring it down to the terrestrial sphere radius via this transformation right here. So this is what relates the 3959 to the same relationship to if you multiply the latitude lines out times the
it'd be like
90 or times 90 from Polaris to the equator. You get the exact same relationship in nautical miles. This is why this is equivalent, because the 6290 is not a radius value. It's just the distance of what it would be in elevation if you multiplied it out based off of using like the same relationship of a sphere of 3959 to move at 69 miles per degree. Same exact equivalence.
Right, because if you're starting at the center of the Earth in terms of where the fictitious observer is, it would be 3959 until you hit the surface. I got you. Kind of get what you're saying. Yeah, I found this paper. I don't know if you see it in main chat. It was just going over that, like how it says, for our purposes, the celestial sphere can be constructed of arbitrary radius. Here to be shown as AK. And then you see that little picture there?
Yep.
Yeah, okay. I see what you're saying.
Yeah, they say arbitrary radius, but to make it useful for terrestrial navigation, it's tied to the geocentric coordinate system transformation, which ties it to this right here. So it's like it's arbitrary using air quotes, but it's also mandatory to be useful for this one.
Right. Which is why it's always geocentric in terms of the reference point.
Yep.
In order for it to be usable or feasible.
Yeah, anything else wouldn't relate to the terrestrial sphere in the way that they've mapped it using the 15 degree per hour ground position of it.
Gotcha.
I put some good videos in chat there.
Dude, yeah, you put some awesome diagrams in here. These are fantastic.
Stealing these.
Yep. That's what we're talking about, the equivalence of, so like the mathematically, the graticule dimensions represented planarly. That's what we're talking about with 6210 as the ceiling.
Yeah, and they'll never acknowledge it or whatever, and they're all like, remember when they used to all be like, "What's the altitude of the sun?" That used to be like the big gotcha when I was young in flat Earth. They would be like, "Tell me the altitude of that star, young man." Like, I'm like, I don't know, man. Any number I give, you're gonna hang me. But no, the answer is this. It's the same thing. And they're like, no, it can't be, because if I draw a triangle, it doesn't matter, dude. If you draw a triangle, it only intersects for two people for terrestrial navigation. Then that's all it's used for. So like, it's a two-party system. That's how the Royal Society designed it. If you want to start to intersect for everyone, moving it out to infinity is just a role play. Nobody can measure that or confirm it. That means absolutely nothing.
It makes it meaningless when you extrapolate it out like that. It makes it just like a useless way to make any assertions about the ground beneath your feet. Especially like knowing that we see, like that we have a perspective limit, that there's a resolution limit, and you're a single point in the center of an outgoing resolution limit. You necessarily see like this in a sphere. That's how it has to work. And so knowing that, if you extrapolate the distances out to infinity, you can't use that to make a meaningful assertion about the shape of the ground beneath your feet.
Nope. Or the motion of the Earth in between. How crazy is that, dude? They based their insane angle of 89.9999999999999 on a distance of 182 million miles or whatever. And they're like, yeah, we can just extrapolate that out to what would that be, like billions and billions and billions of miles when they do it into light years? It's ridiculous.
Yeah, and the light just goes forever to get to you.
Don't forget, it's infinite and goes forever, and also arbitrarily large.
It's infinite, and it's also traveling in a curve, but it's straight until it hits and then it curves.
Curvilinear, dude. It's curvilinear.
It's a parallel line.
That's crazy.
It makes a perfect triangle to the star. Even gravitational lensing, it ignores that and just goes straight to the star. Arcs. Yeah, dude, it's so backwards what they have justified in terms of trying to draw a triangle to things in the sky. Ooh,
yep.
That's classic, dude. Those triangles will get you. They'll get you.
If you notice, we argue this all the time. You hear Alan talk about 6210, 6218 in like every stream and every debate we've ever been in. So this is what we're always referencing, this equivalence, this thing where we're talking about Stellarium. We can use it for either model. It's just sky observations with a relative reference point. That's all it is. That's what we keep saying. That's what we argue. Here it is.
Plane radius. Okay.
Hey, real quick, when we used to go to planetariums, little did we know that we were really actually experiencing reality.
How dare you, Lily? How dare you?
All right. That was awesome and actually kind of clarifying for me for a couple things. Because like I understood it, but like seeing it, like, yeah, helped me a lot actually. Where's that quote, baby? Ended on that quote. Or whatever.
Seeing is believing. Ray Charles. Lily, take us out on an ad for Brushtail Coffee. If you wake up in the morning and you're ready to go to work, and you're like, oh, can't quite leave yet. I'm not ready to face the world. I need a little boost. You might need some Brushtail Coffee. Lily, where do you go to get Brushtail Coffee?
Well, brushtailcoffee.com. I forget. Whoops. Anyways,
it's brushtail.coffee, but you're this close to being fired, but continue.
I'm sorry. I did get the correct Twitter X handle, though, if you guys are on Twitter watching this. Well, yeah, I mean, Brushtail will definitely give you a boost in the morning, but it can do way more than that because it did so for me. And my latest adventure was that I was invited to this wedding and I wanted to be really fancy because it was going to be a fancy wedding, some rich people, etc. So I was like thinking, oh, I should do a really fancy hairdo to go to the wedding. But then the hairdo actually involved long hair. So I was like, what do I do now? Because my hair's not that long. And so I thought, hey, you know what? What the heck? I just sprinkled a little bit of Brushtail Coffee on my scalp and then I washed it off a couple hours later. And I woke up in the morning and guess what? My hair was all the way past my waist. And so I was able to make that beautiful hairdo and go to this fancy wedding, and everybody praised my hairdo. So that's my latest adventure.
Are you telling me Brushtail does full hair restoration now?
Well, hold on. I mean that is a claim. That is a story. Brushtail may or may not endorse the claim, but it is a claim. Wow.
That is something that may or may not have happened.
Personal experience, okay? People can take it or leave it.
Now, for those of you, these are not paid testimonials. These are just everyday average users here, folks.
Brushtail taught me how to love.
I mean, if you're not putting Brushtail Coffee on your head, are you really a true coffee drinker?
Don't even talk to me unless you rinse with brush tail twice a day.
I feel like somebody
Don't
should quickly say, like, brush tail takes no responsibility for people who burn themselves with the.
We need you to do that. We need you to do that, Shane.
Yeah. He can do it
No, oh,
naturally, Shane.
All
Shane,
right, we're gonna
it'll be
wrap
so
up for
natural
the
for
night.
Shane.
Yep, good times.
Yep.
Stellarium.
Oh, shout out to Shalom Shire Farm. Thank you, good sir, for the coffee tip. Speaking of coffees. All right, we will be live again on Friday, I think, and then also on Sunday on Globebusters, where Man of Stone will be presenting something from his channel that he's done before. He'll be breaking down one of his videos. So join us Sunday for a Man of Stone breakdown on Globebusters and Friday for the community Twitter space.